Okay, now for the resource access protocols. Resource access protocols is a topic that's related to operating systems, because operating systems have to cope with one particular problem and they have to take that problem into account. That problem is resulting from the fact that we have seen earlier that we have the notion of so-called critical sections. You should remember that critical sections are sections of code at which exclusive access to some resource must be guaranteed, and we can do this with semaphores or mutexes. And just to remind you, we might have two tasks or processes for which we must be guaranteeing mutually exclusive access to some resource, and then we can use these semaphore operations to guarantee this mutually exclusive access. So either we grant access to that resource, or the thread, process, or task has to wait until that resource becomes available. And if it becomes available, one of the waiting threads, tasks, or processes is woken up and will continue its execution. And this is the release of the resources. So that is something that we have to use if we are having shared resources. Now, as a result of that, in combination with the fact that we are using preemptive scheduling, we are having one effect that must be taken into account. And I'm going to introduce you to that particular effect. Let's assume for the time being that we just have two different tasks. These could also be processes or threads. Let's assume that we have two different tasks. And the priority of task 1 is assumed to be larger than the priority of task 2. And we assume that this task 2 initially becomes executable, so that means it's available for execution, will be executed and will execute for some time. And then at the time t0, it will execute this P of S operation, which means now we are entering such a critical section. Now at time t1, this higher priority task might also become executable, and since we are assuming preemptive execution there, preemptive scheduling, that higher priority task will execute, and at some time then will execute also a P operation for the same resource. Now since that resource is already granted to T2, we have to stop in the execution of that task T1 and resume the execution of T2, where T2 will then execute for some time. Finally, hopefully, there is a release of that resource. If not, we are in deep trouble anyway. So we assume that there is a release of that resource, and at that time, we can wake up T1, and T1 can execute its critical section and finally release that resource as well. So in this case, we see that we have a higher priority task, which is blocked by a lower priority task because it's accessing the same resource. So it's an inconvenient situation, but there is a nice aspect of this rather bad news. The nice aspect is that the length during which this blocking can happen is bounded by the length of the critical section of this lower priority task, which is nice to know because programmers are requested anyway to keep their critical sections short as possible, because we know that otherwise the response times will suffer. So therefore, it's not nice, but we know that there must be a reasonable upper bound. However, in the general case, such a nice upper bound does not exist, as can be shown if we consider a system with more than 2 tasks. Let's assume that we have a system of 3 tasks, and we have in this system 3 different tasks, the priority of each task being higher than the priority of the next task. And let's assume that we have such a situation where initially we start the execution of task T3. We execute the P operation for some resource there, and we are in that particular critical section. Then this task T2 becomes executable again, or becomes executable, not again, and will execute. It's not in any critical section, but then we assume that T1 becomes executable as well. It executes its regular code, but then also generates this P of S operation, and will start to sleep, will start to wait until it's woken up. Now we execute the task with the next lower priority, and this is the task T2. And this task T2 will prevent the execution of task T3, which means there will be no progress with respect to the execution of that critical section. And therefore, it can happen that this blocking goes on for quite some time until finally we resume the execution of T3. And only then will we work on this critical section and finally then hopefully release the use of that resource, and then this task T1 can execute. So we see that in this case we cannot provide an upper bound on the length of this inconvenient situation, on the length of this situation in which a lower priority task is blocking the execution of a higher priority task. And this is what we are calling priority inversion. We can discuss whether or not the case with two tasks can also already be called priority inversion. Traditionally, it's not really called priority inversion, even though the case is already very inconvenient as well. So next, I'd like to demonstrate that this situation is not an academic situation in its negative sense, but that this situation has already happened in situations that are very visible, that have been very visible and that have been very costly. Such a situation happened in the case of the Mars Pathfinder, where according to the report, the following happened. But a few days into the mission, not long after Pathfinder started gathering meteorological data, the spacecraft began experiencing total system resets, each resulting in losses of data. The press reported these failures in terms such as software glitches, and the computer was trying to do too many things at once. So what had actually happened? Well, in the Mars Pathfinder, there is a VxWorks operating system that provides preemptive priority scheduling of threads, and the tasks in the Pathfinder were executed as threads with priorities that were assigned in the usual manner, reflecting the relative urgency of these tasks. And then in the Mars Pathfinder, there is a shared memory area, which was called information bus. And in this shared memory area, it was possible to exchange information there between the different tasks. And now there was a total of at least 3 different tasks. There was one task called the bus management task that ran frequently with a high priority to move certain kinds of data in and out of the information bus. Access to the bus was synchronized with mutual exclusion logs with mutexes. Because obviously if you move things in and out of that shared area, and if you do this in an unsynchronized way, then you will get a very inconsistent state of what's recorded there in this shared area. So therefore, it's needed to use mutexes here. In addition, there was a meteorological task that was gathering data. It was running as an infrequent low priority thread, and it was publishing data there on the shared memory area. And when it was publishing the data there in the shared memory area, it was acquiring a mutex to the right there onto the bus and then release the mutex. And also there was a third task that was available there. It also contains a so-called a communication task that ran with medium priority, and I'm assuming that this task was handling the communication down to Earth. So we see that there is a total of 3 different tasks there. one that's in charge of the retrieval of data from the shared memory, one that's in charge of the communications, and one that's in charge of collecting this data. So all the ingredients that you need for having priority inversion are available there. As a result, the following happened as reported on this public website. However, very infrequently it was possible for an interrupt to occur that caused the medium priority communications task to be scheduled during the short interval while the high priority information bus thread was blocking, waiting for the low priority meteorological data thread. In this case, the long-running communication task having higher priority than the meteorological task would prevent it from running, consequently preventing the blocked information bus task from running. After some time had passed, a watchdog timer would go off, notice that the data bus task had not been executed for some time, conclude that something had gone drastically wrong, and initiate a total system reset. So there was this timer that started, that went off, realized that a task that was supposed to run at a certain interval was not running, and then the whole system was reset and the data was lost. So this demonstrates that this is not some academic example in the negative sense, but that this actually happens in practice. Now, how can we cope with this situation? Well, the first solution would be to disallow preemption while we are executing critical sections. So that is shown over here. We could have a situation where initially we are executing T3 in a normal way. Then the T3 would be executing a critical section, but soon after T3 entered the critical section, T1 would become available. But now, if we assume this approach, then T1 would get blocked until finally T3 would release this resource, and only then could this T1 continue to execute, and after some time we would also have an access there to that common resource from some other task. So in this case you see that this high priority task T1 is blocked for quite some time, even though there isn't really the need to do so. So we would drastically reduce the responsiveness of our system because even high priority tasks could not run even if they are not linked in any way to the shared resource. I think that's pretty clear that this is not a very nice approach. So therefore, we have to look at other means of coping with this effect. And one way of coping with this effect is the use of the so-called priority inheritance protocol. The priority inheritance protocol works as follows. In the priority inheritance protocol, tasks are scheduled according to their active priorities, well, as usual. Tasks with the same priorities are scheduled first come, first serve, well, also as usual. So now let's assume that a particular task is executing a P of S operation, and let's assume that we grant exclusive access to that exclusive access has been granted to some other task. Then, as usual, this task T1 will become blocked. That's a normal way. However, if we observe that the priority of that task that is having access to that resource is less than the priority of the task that has a higher priority, in such a situation, the task with the lower priority will inherit the priority of the task with the higher priority. And then this task T2 resumes, but it will do so at the higher priority. It will do so at the priority of the task that it is blocking. As a rule, whenever we have such an execution of such a P of S operation, a task will inherit the highest priority of the task blocked by it. Yeah? So it could be that we have several accesses to such shared resources. It could happen that we have several tasks with different priorities, in such a scenario, we will always inherit the highest priority of the task blocked by it. Now this means that in certain cases we will be increasing the priority. In order to have a reasonably working system, we also must be decreasing the priority. Whenever some task T2 executes a V of S operation, its priority is decreased to the highest priority of the task blocked by it. It could happen that a particular task for which we have raised the priority is no longer blocking other tasks, and then of course we have to decrease the priority. So if no other task is blocked by a particular task, then we are decreasing the priority to the original value. And in any case, the highest priority task among all the executable tasks is then ratio. There is one final item on the slide, which makes the implementation rather complicated. The inheritance of priorities is transitive, which means that if T2 blocks T1 and T1 blocks T0, then T2 should inherit the priority of T0. And that also applies to a larger set of tasks. So now let's look at how our system is actually handling the situation that we have seen earlier. So let's look at this situation where we have this task T3 that's executing without actually having access to some shared resource. Now it's executing the P of S operation, and now T2 becomes executable, and we execute T2, and now T1 becomes executable, and at this time T1 executes the P of S operation. Now that means we are still putting T1 to sleep, like before, but now T3 will inherit the priority of T1, which means that T3 will execute at a higher priority, and therefore it will not be T2 that will now run, but it will be T3 because it has the higher priority. Therefore, we are now executing the critical section there for T3, and after releasing the resource, we will continue the execution of T1. Now also working on the critical section there, and once T1 has completely finished its execution, we will be able to execute T2. So in this way, we are inheriting the priority. There is also an animation module. There is a simulator that we can use to demonstrate this operation, but I'm not demonstrating this in the lecture today. We will do this a little later. I'd also like to demonstrate that we can have nested critical sections. We can have a situation that is more complicated than the one that I just showed on the previous slide. Let's assume that we have a task T3, which first of all is accessing a shared resource A, and correspondingly is requesting mutually exclusive access here. And then we can assume that this very same task is also accessing another resource, and we are accessing mutually exclusive use there as well. Now we assume that there is a task T2, which initially is running as outside any critical section, but then is also requesting mutually exclusive access to that resource, which cannot be granted, so therefore we now continue the execution of T3. And at this time we are raising the priority of T3 to that of task T2 because we are now blocking task T2. We are executing that task, and now we assume that T1 is becoming available. We are executing T1 because of its higher priority, but now T1 is also requesting access to that resource protected by A, which means that at this time we are resuming the execution of T3, but now T3 is inheriting the priority of task T1. Now we are executing this task T3 there. At this time we are releasing the resource protected by B, But that doesn't change the priority because B is held by task T2, which has a medium priority, so therefore the priority is not changed there. But when T3 is releasing that resource as well, the priority will change. It will drop to the very bottom priority because we are not blocking any other task there. And therefore, among all the different tasks, that task T1 is now the one that has the highest priority and will be executed. Now, next I'd like to demonstrate transitivity testness for this priority inheritance. So we have a situation similar to the previous one, but still slightly different. So we start the execution of T3 over here, request exclusiveness there for using B. Then we assume that T2 becomes executable as well. And we request another mutually exclusive access there, and request another mutually exclusive access there, and there at this time we have to wait because that resource is already in use. So we resume the execution there of T3 until T1 becomes executable. So at this time, we are running with the priority of task T2 because we are blocking task T2. Now over here, we are requesting mutual exclusiveness there with an access to A. Now at this time, we are now also blocking task T1, so therefore this task is now raised in its priority. Because in this situation, we have a scenario where this task T2 is blocking the execution of T1, and T2 has a higher priority than T3. So therefore, we have to refer to this transitivity, which means that we have to take into account that indirectly this task T3 is now preventing the execution of T1. It's not just preventing the execution of T2, even though it's sharing resources only with T2, but indirectly it's also blocking the execution of T1. And therefore, the priority at this instance in time is raised to the priority of T1 and not just to the priority of T2. Now, if at this time we are releasing one of the resources, we are breaking this chain of dependencies, and we can think about which task we are still blocking at that time. If we are releasing B, then we are not blocking T2 anymore, and therefore this whole chain is breaking, and there is no dependency to T1 left either. So therefore, the priority is reset to the initial priority. Okay? So that's how we have to take into account such a chain of dependencies. Now we see a number of advantages of this priority inheritance protocol. We have also seen that certain aspects of the protocol are difficult to implement, and there are also certain limitations and problems with the protocol. So using this slide, I'd like to demonstrate that we can still have deadlocks. And in order to demonstrate the existence of deadlocks, we're starting with one task T2 that can be executed over here. We're executing that task. We are requesting the exclusive access to this resource B. Now we are starting the execution of T1. We are requesting the access to resource A, and now we are requesting access to B as well. At this time, we cannot continue the execution of T1 because B is already held by that other task. And now we assume that we execute the critical section there for task T2. And if in this execution we are now also requesting the use of A, the whole system gets blocked. So I think a more easy to understand visualization of that situation is this one, where we see that initially we have executed this statement over here, and then we have executed this statement over there. We have then executed that statement over there, and then we see that we have these cross-coupled dependencies over there, where we have this resulting situation where T2 cannot continue because it's requesting access to A, which has already been granted, and T1 cannot continue because it's requesting the access to B, and B has already been granted to T2. So therefore we have this mutual dependency, and none of the two tasks can continue, and we have a deadlock. So obviously, even with the priority inheritance protocol, a deadlock is feasible, but we have to admit that this problem also exists if we don't use priority inheritance. So it's not resulting in this case from priority inheritance. It's only that priority inheritance is not avoiding this deadlock problem. And there, of course, it would be nice to have, for example, a different model of computation that would avoid that problem. So next, I'd like to demonstrate that with priority inheritance, this problem on Mars was also solved because they did ship the full operating system VxWorks there to Mars, including all the debug primitives and including the calls to these mutex primitives. For these mutually exclusive primitives, there is one parameter that's available for VxWorks that allows you to turn the priority inheritance protocol on and off. When the software was shipped, it was set to off because the designers assumed that in this way the operating system would just cause less overhead. They wanted to minimize the overhead, therefore they turned priority inheritance off. Now fortunately, they did also ship the debugging facilities there to Mars, which is a little unusual because I think nobody could assume that any human could, debug the system there on Mars. But nevertheless, they shipped the debugging facilities there to Mars. And using these debugging facilities there, they changed that particular parameter. They changed it from off to on. So using the debugging facility, they modified the values there in the memory. And they knew, of course, the values in the memory. They knew exactly where these parameters were stored. And they changed them so that while the system was already deployed on Mars, they turned priority inheritance on. So in that way, they solved the problem with the Mars parse-finder. There are some remarks on the priority inheritance protocol. It could well happen that as a result of using priority inheritance, that many tasks are running with a very high priority. I think you can imagine that there could be a situation where many tasks are requesting access to a common set of resources, and if all of them are requesting access to a common set of resources, in the end, it's very likely that all of them will run with the highest priority, which of course is not very nice. We see that deadlocks are still possible. There are certain papers that discuss the limitations and the problems with that protocol. So this guy over here, a guy associated with FSM Labs, has some arguments against priority. His main argument is that, well, implementing priority inheritance is more complicated than it seems because considering this transitiveness for the dependencies between the different tasks is a problem, and he argues that if you actually need to use the priority inheritance protocol, then the design of your system is already fooled right from the beginning, and you should try to design your system in such a way that you don't need priority inheritance. Nevertheless, priority inheritance in some way finds applications in languages that have been used in a rather widespread manner. For example, we discussed Ada as a language that is applied to real-time systems. There in Ada, during the rendezvous, the task priority is set to the maximum, so that we have a somewhat restricted version of priority inheritance here. There are also protocols that handle special cases, like, for example, the special case of a fixed set of tasks where all the tasks are already known at design time. There we can use the so-called priority ceiling protocol. So this leads me to the summary of today's presentation. I have started with a general discussion of the requirements for embedded operating systems. I looked at configurability, at the possibility to have I/O not implemented via privileged instructions. And we also looked at the possibility to have interrupts directly connected with software and not all restricted to be used by the operating system. Then, as a special case of embedded operating systems, I looked at real-time operating systems, which are embedded operating systems that also must meet real-time constraints. There I looked at the different requirements as well. We looked at the need to provide timing predictable services. We also looked at time services. We saw that synchronization might be needed. We looked at the different classes of real-time operating systems. And we looked at how device drivers can be embedded into such operating systems. And finally, I discussed priority inversion. I discussed the problem, and I discussed priority inheritance as one protocol that we can use to get around these problems. So this concludes today's lecture. Thank you very much.